Hello everyone, my name is Jie. I am a PhD student from University of California, Merced. Today I will introduce our work, HMANN, Efficient Billion Point Nearest Neighbor Search on Heterogeneous Memory. This work is published in NewIPS 2020. Nearest neighbor search is widely used in image and documentation retrieval. Nearest neighbor search in a high-dimensional and large-scale dataset is highly challenging. The search system stores billions of data points offline with the indexing algorithm based on the distance relations. Given a query point, the nearest neighbor search calculates the distance between query and data points and returns k nearest neighbors. Approximate nearest neighbor search algorithm has been proposed to address the issues in terms of search accuracy, computation efficiency, and memory consumption. Graph-based methods build a navigable graph over base point. Each point in the graph is a vector in the dataset. As this figure shows, the search of the graph-based method starts from a specific point and finds the nearest neighbor based on the connection of the navigable graph. Take HNSW as an example, which contains multiple layers of navigable graph. The bottom layer, or layer 0, contains all the database elements, and the above layer are randomly selected nested subset of the data point elements. HNSW starts the search at the top level and performs one greedy search until it reaches the nearest neighbor of the query in that layer. The node is then used as the entry point in the next layer to start the search again. At the bottom layer L0, which contains all the elements, HNSW performs a best first beam search to get the final candidates. Graph-based methods achieve high recall and low latency. However, it cannot host billion-scale data points since it requires large memory consumption for both data points and connection information. Compression-based methods compress data points to fit memory capacity and cluster the compressed data for searching. However, such method leads to low search accuracy. The state-of-the-art billion-point nearest neighbor search combines both graph-based method and compression-based method, and it leverages the large capacity of the SSD to store data points and achieves high recall. However, it has high latency due to the expensive SSD accessing time. It is natural to ask, can we have a fast and accurate approximate nearest neighbor search algorithm for extremely large-scale dataset search? Heterogeneous memory is promising to solve this problem. Heterogeneous memory combines a high-capacity memory technology such as PM and a high-performance memory technology such as DRAM. The slow memory, or PM, performs 80 times faster than SSD, but it's still 3 times slower than DRAM. Therefore, SSD-based approximate nearest neighbor search or existing approximate nearest neighbor search with naive data placement strategy can hurt the search efficiency badly. The design of HMANN generalizes from HNSW, whose hierarchical structure is naturally fit to the heterogeneous memory. Elements in the upper layer consume a small portion of memory, making them good candidates to be placed into fast memory. The bottom layer are all elements and has the largest memory consumption, which makes it suitable to place into the slow memory. However, in HNSW, The majority of search happens in the bottommost layer, which means it will happen in slow memory. The key idea of HMAN is therefore to build a high-quality upper layer and make most memory accesses happen in fast memory, in order to provide best navigation for search at the bottom layer and reduce the memory accesses in slow memory. In this paper, we propose HMAN, which takes both memory and data heterogeneity into consideration, and enable billion-scale similarity search on a single CPU node without using any compression technique. Our evaluation result shows that HMAN achieves 95% of recall in less than 1 millisecond on CPU. HMAN achieves logarithmic search time complexity and linearistic indexing time complexity, which match that of the state-of-the-art solution. The indexing of HMAN outputs a navigable graph with high search quality, which contains 4 steps, including top-down insertion, sorting, deleting, and bottom-up promotion. HMAN indexing algorithm passes the whole dataset 2 times. The top-down insertions of HMAN build a navigable graph incrementally. HMAN insert the element from the top layer to the bottom layer. After the top-down insertion, HMAN builds a theoretical graph G with L layers. Then HMAN deletes the upper layer of the graph and sort the elements in the bottom layer based on its degree. HMAN promotes high-degree elements from the bottom layer to upper layers to build high-quality search graph. The goal of the search algorithm in HMAN is to minimize the search in slow memory, which include the search from the top layer to the layer 2, the search in L1, and search in the bottom layer. HMAN performs one greedy search from top layer to L2 to find the entry point E in L1. In L1, HMAN will perform ungreedy search, where N is a user-defined parameter as EF search L1. This figure shows an example as EF search L1 is defined as 3. The search will start from the entry point and return 3 nearest neighbor of the query in L1. And then HMAN will perform parallel search with the multiple thread in bottom layer. The search will start from the 3 entry point returned from L1 and get the nearest neighbor of the query as the final result. We test HMAN on a opt-in-based heterogeneous memory. We evaluate HMAN as the query response time and the accuracy of top K recall. We compare HMAN with 2 state-of-the-art billion-scale compression-based methods and 2 state-of-the-art graph-based methods. We measure the above 4 baselines with the opt-in memory mode. This figure shows that HMAN outperforms all existing solutions and obtains top 100 recall of 90% within 4 milliseconds, and the top 1 recall of 95% within 1 millisecond. HMAN is 2 times faster than graph-based method to achieve same accuracy. It also outperforms the state-of-the-art compression-based method in recall versus latency by a large margin, obtaining 46% higher recall under the same search latency. We further compare HMAN with HNSW by using memory mode, first touch NUMA, and the slow memory only environment. The figure shows that HMNN outperforms HNSW with memory mode and first touch NUMA by 2 and 3.7 times. This result indicates that explicitly managing data for heterogeneous memory as HMNN is the key to achieve superior latency and recall result. We further evaluate the effectiveness of HMNN indexing algorithm. HMNN promotes high-degree node from the bottom layer to upper layers. We evaluate HNSW with a parallel bottom layer search without bottom-up promotion. The blue line shows the result. This graph shows that HNSW with a parallel L0 search only slightly outperforms HNSW. The result indicates that without HMNN indexing, the element of L1 in HNSW are selected randomly and sparse, and the entry point found through L1 search is suboptimal. We further break down the performance of HMNN. The figure shows the result. The red line shows the performance of HNSW with obtained memory mode. HNSW plus bottom-up promotion modifies HNSW algorithm, mapping the bottommost layer to the slow memory. The performance of HNSW plus bottom-up promotion shows in green line. The figure shows that the bottom-up promotion slightly impacts the search efficiency. The bottom-up promotion plus the parallel L0 search, which performance shows in purple line, significantly improves the search efficiency, comparing with running HNSW on heterogeneous memory without explicitly data management. HMNN also leverages some system-level memory optimization techniques such as data prefetching to further improve the performance. The black line in the figure shows the performance of HMNN. From this work, we learned that releasing the full power of heterogeneous memory sometimes requires the co-design of algorithm and system. HMNN maps the theoretical design of the graph-based approximate nearest neighbor search to memory heterogeneity in heterogeneous memory. Combined with a set of system-level technique, HMNN avoids expensive access in slow memory without sacrificing the accuracy. Our evaluation result shows that on 2 billion scale dataset, HMNN provides 95% top 1 recall in less than 1 millisecond, which established the new state of the art for indexing and searching billion point datasets. Hope you enjoy this video, and please contact me if you have any questions. Thank you.